Everywhere you look, there are patterns. Many of these patterns are a part of nature. Others are man-made. Sometimes in imitation of nature, sometimes rather more abstract. But what all these patterns have in common is that they are pleasing to the eye. Why should this be? What is it about such patterns that we find so pleasing? The answer is to be found in their structure. They all display a certain degree of symmetry. Such geometric structures are what the geometry stream of this course is all about. Repeating patterns, regular solids, crystal lattices, also friezes, and wallpaper patterns. And tilings. It's not at all like the view of geometry portrayed in the work of Euclid. Geometry was, for a long time, a rather neglected subject. In large measure, this has been due to the tremendous impact which the development of analysis has had upon the whole of mathematics. Great strides were also made in algebra, particularly in the theory of groups, which forms the subject matter of the algebra stream of our course. Now, structure is what the whole of mathematics is concerned with. Logical patterns are to be found in every branch of the subject, and you'll see beautiful examples of that in group theory. But it's an important part of the charm of geometry that the structures it deals with are themselves visible patterns in space. You can see them. In some cases, you can even touch them. Perhaps this tangibility explains the resurgence of interest in geometry which has come about in recent times. So in the geometry stream of this course, we should be looking at geometric structures of a particularly visual nature. Now, three-dimensional structures like this will be studied later in the course. In this program, we shall concern ourselves solely with two-dimensional structures, with patterns in the plane, like this wallpaper pattern. You may be sure we shall find enough to occupy us in analyzing and classifying the possible patterns which arise. Do you have wallpaper at home? If you have, is it something like this? Well, of course, tastes in wallpaper differ. Perhaps you might prefer something like this one. But what does it mean to say that one wallpaper is something like another? How about this? Well, I wouldn't want to pay very much for just a pattern of dots. It's not a bit like either of the other patterns we've seen. Or is it? What's your answer? If you want more time, just pause the tape. My answer is the first one. In fact, from a certain point of view, the dot pattern is actually the same as the first wallpaper pattern. In what way are they the same? Well, it's the underlying structure that is identical. Later on, we shall classify them as both belonging to one symmetry type.
The definition of symmetry type will eventually be stated in terms of groups, the subject studied in the algebra stream of this course. But for the moment, I want to look at it less formally. What I'll do is look at the way the motifs are repeated. If two patterns repeat in the same way, then we say that they're of the same symmetry type. I'll show you what that means. Here is the flower pattern. And here it is yet again, but printed in a different colour on an unusual material, transparent. I'm not sure whether this idea is marketable, but just in case, we've printed our copyright in the corner. You might not like transparent wallpaper. It would defeat the object by showing all the cracks in the wall underneath. But it will help me to show you just what I mean when I talk about the way the motifs are repeated. There we are, they coincide exactly. Now, for example, if I move the overlay upwards by a short distance, then the motifs coincide again. Imagine that the pattern stretches over all the plane right out to infinity, both on the original wallpaper and on the overlay. Then these awkward overhanging bits wouldn't be there. They're not important anyway. What is important is that you should appreciate the way in which the pattern repeats itself, namely when it's shifted upwards. And we get the same sort of thing if we shift it along horizontally. There's yet another way in which the pattern repeats itself. A little bit less obvious may be. If I rotate the overlay by a quarter of a turn, the motifs coincide once more. You get a repetition of the original pattern each time you rotate through a quarter of a turn. So there's a fourfold rotational repetition of the pattern. We'll soon see that the dot pattern also repeats itself in just the same ways. But before looking at that, let's see if there's any other way in which these motifs repeat. The pattern repeats itself in a mirror. The image you're seeing in this mirror coincides exactly with the real pattern behind it. Let me show you a different way of looking at this, what shall we call it, this mirror repetition. It relies on a different way of showing what the mirror image is like without using the mirror. Forget about this half for the moment. If I move the mirror, there's a mark where it used to be. In fact, it's a crease in the transparent wallpaper. If I were to fold this right over along the crease where the mirror was, you'd see the wallpaper back to front, lying over here behind the mirror line. And it would look precisely like the mirror image you can see now. For example, this point would fold over to its mirror image, the same distance from the mirror on the other side. So I can do without the mirror. I can achieve a mirror image by looking at the reverse side of the paper. You've probably observed this yourself. If you look at the wrong side of a color slide, you see the mirror image. So when I said that the motif repeats itself in the mirror, it's the same as saying that the transparent wallpaper pattern coincides with itself when you fold it over. Actually, this is only half the story. The mirror should really be thought of as double-sided. So the mirror image of the top half, that is, the top half back to front, also coincides with the bottom half. So putting that all together, two-way reflection is the same as turning the whole transparency over. And apart from the color, the pattern looks exactly the same as it did before. We've now seen several different ways in which the motif repeats itself. Mirror repetition just now, rotational repetition through a quarter turn, and translational repetition, both horizontally and vertically. Are there any more? Well, yes, there are mirror repetitions in vertical lines too. Imagine this to be where the mirror comes. So this is our axis of reflection. I have to put the axis back where it was, and when I do, the motifs coincide. Incidentally, the axis could also be positioned to pass through the centers of the flowers instead of in the gap between the flowers. And that's also true of the horizontal reflection. There are horizontal axes, both between the rows of flowers, as we saw earlier, and through the flowers. And finally, there are mirror repetitions in diagonal lines through the flowers. And similarly in the other diagonal direction. I'm sure you can see the reflectional symmetry here without my having to flip the transparency over again. And that does it. To summarize, the different ways in which this pattern repeats itself are as follows. Translational repetition, both vertically and horizontally, rotational repetition through 90 degrees, and reflectional repetition in 4 directions.
What of the dot pattern? Does it repeat itself in all of those ways? If it does, then we shall say it is of the same symmetry type. So let's check it out. First, the translations. Vertical, yes. Horizontal, yes. And then we have to check for rotations through a quarter of a turn. Yes, we get the same fourfold rotational repetition. And now the reflections. First of all, in a horizontal line. Yes. And then in a vertical line. Yes. And then in a diagonal line. Now I think you can probably see the reflectional symmetry in this line without my having to turn it over. And then, of course, there's the other diagonal. And again, if you look along the axis, you can again see that it'll work out. They all check. So the dot pattern is of the same symmetry type as the first wallpaper.
So, a symmetry type is determined by the various ways in which the pattern repeats itself. That's our informal definition. From what we've seen, we therefore say that the dot pattern has the same symmetry type as the first wallpaper pattern. How about the third wallpaper pattern? We can look to see if it has the same symmetries. Well, we can translate it vertically. That's okay. And horizontally. That seems fine. What about rotation? We can rotate it, again by a quarter turn. Just as with the other two patterns. What about reflections? Let's try reflecting in a line through the centre. I'll put the axis back where it was, but it doesn't seem to work. Perhaps I made a bad choice of line. Well, it's not that. If I move the back-to-front transparency to one side, I think you can see the trouble. The original motifs are clockwise, and the mirror image ones are always anti-clockwise, so the two can't possibly coincide. It's true that this third wallpaper has some of the symmetries of the first two, but it doesn't have them all. So therefore, we have to conclude that it's of a different symmetry type.
So far, our approach has been deliberately informal. Now, we've spoken of symmetries. Let me ask you something. What do you remember about the set of all symmetries of an object? Yes, of course. The answer is, it's a group. Now, we can see this by checking for the properties of a group. What's required is, if two symmetry operations are performed in succession, the result must be another symmetry. And also, if any symmetry operation is reversed, the result must again be a symmetry operation. First of all, then, I shall look at the composition of symmetries. I shall perform two symmetries, one after the other, on the first of our wallpaper patterns. I'll start with rotation through a right angle. And then I'll translate upwards. And you can see the pattern ends up coinciding with itself again. In fact, the same argument can be used to show that the composition of any two symmetries will again be a symmetry. Let's look at that in an action replay. Whatever symmetry operation is performed first, the pattern would be unchanged at the end of it. And so the second symmetry operation, which was possible by itself, will still be possible after the first operation. And it too will leave the starting pattern unchanged. It will still coincide with itself. So the composite leaves the pattern unchanged, and therefore the composite is a symmetry. That's the first property. Now for the inverse symmetry. Will that always be another symmetry? Well, to find out, all we have to do is to play the recording backwards. Of course, a reverse symmetry takes the pattern back to its starting position. And so it again is a symmetry operation. And that's the second property. And the two properties together tell us that we have a group. So when we say that two patterns are of the same symmetry type, we mean, in conventional mathematical terms, that they have the same symmetry group. And that's true, as we saw, for the first wallpaper pattern and the dot pattern. Their symmetry groups are the same. In contrast, as we saw, the symmetry group of the clockwise pattern is not the same as the first two. It has no reflections. So that's two different symmetry types we've seen so far. There are, of course, infinitely many different wallpaper patterns. However, if we classify them in terms of their symmetry type, we discover just 17 classes. There are precisely 17 distinct symmetry types of wallpaper pattern. Well, we've seen 2 so far. Let me show you just 1 or 2 more. All wallpaper patterns must have translational symmetry in 2 directions. Otherwise, you wouldn't be able to repeat the motif over the whole plane. But what else can you have? Well, this one is interesting. It's a bas-relief wallpaper with a hexagonal pattern. It has rotational symmetry through 1/6 of a turn. And you can visualize that for yourself. If you rotate clockwise 1/6 about the center of any hexagon, then the result will coincide with the original. This bridge going over here will move to coincide with this bridge over here, and so on. So we have 6-fold rotational symmetry. But what about reflections? Let's ask Fred to use his mirror on a copy of this.
Going round a hexagon clockwise, the strip I'm travelling on bridges over the next strip, which in turn bridges over the next strip, and so on. Whereas in the mirror, my finger is going anti-clockwise to bridge over. Now, if my finger goes clockwise in the mirror, then each strip it travels along is an underpass instead of a bridge. So the mirror image is not the same as the original. And that's true wherever you place the mirror.
So, like the earlier clockwise flower pattern, this one has no reflectional symmetries, just translational and 6-fold rotational symmetries. Of course, you can have a pattern with 6-fold rotation that does have reflectional symmetries. You'll see one in a later section of the program. To end this section, I'll give you just one more example. This one differs in a quite subtle way from one you've seen before. It's got 4-fold rotational symmetry, like the first pattern. You can take the center of any one of these dark shapes, and it'll be a center of 4-fold rotational symmetry. And it also has reflectional symmetry, but this time in only 2 axes instead of 4. It has a vertical axis of reflection. That's because as you go across the pattern, you get a dark motif and then its mirror image alternately. Now this one has a clockwise nature, then anti-clockwise, then clockwise, anti-clockwise, and so on. And the same thing happens if you go down the pattern. Clock, anti-clock, clock, and so on. So there's also a horizontal axis of reflection. But it's impossible to find any diagonal line which will reflect a clockwise motif to coincide exactly with an anti-clockwise one. So that's 4 symmetry types of wallpaper patterns. And later on, we'll look at some more.
Let's now turn our attention to another way of looking at patterns in the plane, one that we haven't considered so far. I'm going to look at the sorts of pattern we can get by covering the plane with tiles, the sort of thing you do to your bathroom wall. Tilings are in the first unit of the course, and also form the subject of another unit. Of course, some tilings aren't very exciting at all. Others are in an altogether different league. This is the Alhambra Palace in Granada, Spain, built by the Moors in the 14th century. The Islamic reluctance to depict living forms led the Moors to explore purely ornamental patterns in the greatest of detail. It has to be said straight away that tiling patterns fit into the general framework of wallpaper patterns. You can always print a tiling pattern onto paper and use it as a wallpaper. In fact, we did precisely that for one of our wallpapers. As a matter of fact, the Islamic artists of the Alhambra managed to represent all 17 wallpaper pattern types with their tilings and other decorations. The fact that all 17 types existed in the Alhambra had been rumoured for a long time, but it was finally confirmed only recently in 1986 by a Spanish mathematician, Rafael Gomez. So we can work out the symmetries of a tiling pattern just as we can with any other wallpaper pattern. But tilings raise a lot of new questions as well. Suppose you did want to tile the wall around a shower in your bathroom. What shape of tiles would you choose? Well, you obviously don't want to leave any gaps. It wouldn't look right. But more importantly, it would defeat the main object of the exercise, which is to prevent water from soaking into the plaster underneath. So you want to choose tiles that fit flush together. Squares are obvious. That's the usual shape for bathroom tiles. These circular ones obviously aren't any good. And as for these octagonal tiles, well, it's just not possible. But one thing you can do, you can arrange that the gaps are all squares. So if you use square tiles as well, then you can tile your wall properly. In fact, although I've never seen this arrangement on a wall, you do sometimes see it on stone floors. I expect you recognize the similarity with our floor, which doesn't have equilateral octagons, but still does have octagons and squares. Now what about hexagons? These regular hexagons will work all right. Parallelograms work too. You can make strips out of parallelograms and then add more strips above and below. But as a matter of fact, with these particular parallelograms, there's another arrangement. These are 60-degree rhombuses. 3 of them fit together to make a hexagon. And we've already seen that hexagons work. And equilateral triangles work too.
In general, there are all sorts of possibilities for tilings. We've even decorated the studio with some unusual tilings. Some with a single repeated tile, and some with more than one shape of tile in the one tiling. In the first unit of the course, you'll look in detail at 2 particular classes of tilings. Firstly, the Archimedean tilings. These are made up of equilateral triangles, squares, and in fact, any combination of regular polygons, but with one proviso. At each vertex, you must have the same arrangement of tiles as at every other vertex. You've seen an example already, with octagons and squares. At each and every vertex, we get 1 square and 2 octagons meeting, and there are no exceptions. We label this tiling 488 to indicate the 1 square and the 2 octagons. There are actually 11 different types you can get that way, which you'll see in the text. But let me just show you a second type here. Equilateral triangles and hexagons. And around each vertex, there are now two triangles separating two hexagons. Triangle, hexagon, triangle, hexagon. And again, this is true for every vertex. The other class of tilings, which is discussed in the first unit, are the lavus tilings, after the early 20th century German scientist Fritz Lavus. To get a lavus tiling, you first take an Archimedean tiling, then put a dot at the center of each tile. Now, draw lines between dots centered at adjacent tiles. And finally, rub out the edges of the old tiling. We get the tiling we saw earlier with 60-degree rhombuses. This lavus tiling is the jewel of the Archimedean tiling that we started with. So there are precisely 11 lavus tilings, the jewels of the 11 Archimedean tilings. In the video appendix for the course, you'll find the jewel construction carried out for all 11 cases. And there are various points in the course where you'll find this useful for referring to. One interesting result of the jewel construction is that every lavus tiling is made up of a single shape of tile. In other words, the tiling is a monohedral. But more than that, a lavus tiling is what's called isohedral. That is, whatever individual tile you're standing on, the pattern looks exactly the same as it does from any other tile.
There's an important difference between the way we classified wallpaper patterns and the way Roy has just been classifying tilings. Whereas wallpapers were classified in terms of symmetries, which are global properties, Roy classified tilings in terms of the arrangement of tiles at a vertex. That's a local property. You could call this the adjacency type, the way in which the tiles fit together. The topic of classifying adjacency type is one of the things you'll study in the first unit of the course. And later on, you'll come to a unit in which the concepts of adjacency type and symmetry type are combined to produce a very detailed classification, resulting in 81 lavus type tilings. And the same process can be applied to Archimedean type to get 91 different Archimedean types. We'll end this program by giving you a brief sketch of what's meant by combining adjacency type and symmetry type. The point is that the adjacency type of the individual tiles is largely independent of the symmetry group of the tiling as a whole. You can see this by taking an Archimedean tiling, for example, and doing things to it that change the symmetry type without changing any of the adjacencies. For example, here's an arrangement of rods into a regular hexagonal tiling pattern. Actually, this is both an Archimedean and a lavus tiling, but let's concentrate on its Archimedean nature. That is, each and every vertex has the same arrangement of tiles around it, 3 hexagons. So its adjacency type is 6, 6, 6. Well, what about the symmetry type? It's got lots of axes of reflection, but the important point for our purposes is that it's got 6-fold rotational symmetry. Now then, I'll keep hold of this end, and Roy, would you please come and take the other end and pull? Well, that certainly destroyed the 6-fold rotational symmetry. There's no rotational symmetry at all. But the adjacency type hasn't changed. Each vertex is still surrounded by 3 hexagons. Look, even here, where 2 edges lie along a single line, we still think of this as a hexagon. It's only got 5 sides, but there's a vertex in the middle of this side, so it's got 6 edges. But now look, if we carry on pulling, No, we've got a brick wall type of pattern. And yet nothing has changed as regards the way the rods are linked together. So the adjacency type is still exactly the same. And now we've even recovered some rotational symmetry. This has twofold rotational symmetry. That's to say, if you rotate by 180 degrees about the center of a brick, the pattern coincides with its starting position again. And this shows that a tiling of a particular adjacency type can still have several possible symmetry types. As I said before, there's a way of putting the adjacency and symmetry ideas together to get a finer classification than either would give alone. It involves group actions, which you'll study soon in the algebra stream of the course.